All right, guys, we're going to go over page 3 of our Unit 9 test review. 6 through 13 say to prove the following statements. So when you're told to prove, you are assuming that all of these things are true, and you have to make the connections showing that you can transform the two sides into a common value. So a lot of times what that means is we're going to start with the more complex side and change it to equal the simpler side. But there are some times where you might make changes on both sides in order to show that they're in fact equal. But again, since this says prove, we are going to assume that both sides are actually equal. So we're going to do this through a combination of all of our identities. So to start with here, I'm going to rewrite secant, cotangent, and sine all in terms of sine and cosine. So secant is the reciprocal of cosine. Cotangent is cosine over sine, and sine is just sine x over 1. So when you look at this, they're all being multiplied, so I can cancel out factors. I've got a cosine in the numerator and a cosine in the denominator. They cancel out. I've got a sine in the numerator and a sine in the denominator. They cancel out. So all I'm left with after all this multiplication is 1 over 1. And so my final, left side equals 1, right side equals 1 is proven true. For number 7, I've got these two binomials, and they're being multiplied, which means I need to FOIL. I need to FOIL these. If you notice, they have matching factors at the front, matching factors at the end, and they have mixed signs, which means this was a difference of squares. And so I can quickly just put it back together as 1 squared, which is just 1, minus cosine squared x. And now that I've kind of re-multiplied that factored form, I've now got 1 minus cosine squared x, which is one of the Pythagorean 7 identities. 1 minus cosine x equals sine squared x. And so both sides equal sine squared x proves that these are equal. Moving to 8, I've got tangent plus cotangent squared. I'm trying to prove that it equals secant squared x plus cosecant squared x. So first thing I notice is that I've got a binomial, and it's squared, which means I'm going to multiply it by itself. And whenever you multiply binomials, you need to use FOIL. So I'm going to multiply the first things together. Tan x times tan x gives me tan squared x. I'm going to multiply the outer things together. So I'm going to get plus tan x cotangent x. I'm going to multiply the inner values together. So I'm going to get plus cotangent x times tan x. And then I'm going to multiply the last things together. So I had 2 positive cotangents multiplied. I get plus cotangent squared x. So long expanded multiplication there. Looking at this like light blue right here, I'm adding tangent times cotangent. Tangent and cotangent are reciprocals, which means when you multiply them together, they just equal 1. And actually looking at this orange section, I've got the same thing. I've got plus cotangent times tangent, so plus 1. Now, what I've done here is I have gotten this kind of broken down into what looks like it could be 2 of the Pythagorean 7s from our hexagon. Okay, so, sorry, let me fix that. 2 of the Pythagorean 7s. This first one, tangent squared x, if you go to your hexagon and you start, if you start at tangent squared x and you follow the 7, you could say tangent squared x plus 1 equals secant squared x. So what I can do is I can take this entire left side and just replace it with secant squared x. And for the next one, if I start in the center of my hexagon and I follow the 7, 1 plus cotangent x actually equals cosecant squared x. And that left side that I just finished simplifying looks a lot like the right side from the original thing I was asked to prove. And so I've proven that these two sides are equal. For number 9, I've got cosecant squared x minus 1. That looks a lot like one of the 7s, one of the Pythagorean 7s. And if you use your triangle, the one that involves cosecant is 1 plus cotangent squared x equals cosecant squared x. Now, this says cosecant minus 1. So if you take this original, okay, this original right here, and you subtract 1, now I've got cosecant squared x minus 1, and it equals cotangent squared x. So what this means is I can rewrite this as cotangent squared x over cosine x. And I'm trying to prove that this equals cotangent x times cosecant x. So this is one of those ones where I probably want to mess around a little with both sides. All right, I probably want to mess around with both sides a little bit. So on both of these, I'm going to rewrite them in terms of sine and cosine. So I'm going to take my cotangent and I'm going to rewrite it as cosine squared x over sine squared x divided by cosine x. And I'm going to go ahead and just write that as cosine x over 1. And then that equals, cotangent is cosine x over sine x. And that's multiplied by cosecant, which is the reciprocal of sine x. So right now I'm kind of messing around with both sides, seeing if I can simplify them a little bit. And so for this first side, I've got a fraction divided by a fraction. So I'm going to keep, change, flip. I'm going to keep, change, flip this whole thing. So I've got cosine squared x over sine x times, and I got to flip the second, 1 over cosine x. So what that's going to do is this cosine and one of these will cancel. And that's going to leave me with cosine over sine, which is cotangent. Now on the right side, I've got, wait, did I do something wrong? Hold on just a second. Cosine over sine, keep, change, flip, keep, change, flip, sine over cosine. Yes, sorry, 1 second. I forgot to square this. Sorry about that. So now that's multiplied by 1 over cosine x. This will cancel. One of these will cancel. And it leaves me with cosine x over sine squared x. Okay. Now, with these two, I'm going to multiply across. And cosine x times 1 equals cosine x. And, sorry, I'm running out of room. And sine times itself equals sine squared x. So we were able to prove that those two sides are equal. Make sure that if you have your exponents that you keep them throughout. That's where I messed up. All right, a couple left. Well, 4 left. All right, for number 10, we are trying to prove that this left side equals 1. These two fractions are being added, so I want to start by writing them in terms of sine and cosine. So secant is the reciprocal, and then I'm going to add that to sine, and then I've got cosecant, which is 1 over sine x. I'm trying to prove that these equal 1. So for both of these, I'm going to keep, okay, pen is messing up now. I'm going to, keep, change, flip, keep, change, flip. And so what I end up with here for this first one is I've got cosine x over 1. That's my keep. Change to multiplication and flip my denominator. So that's my keep, change, flip. I'm still adding. I'm going to keep sine x and change to multiplication and flip this guy. And so now what I've got is cosine x times itself over 1 plus sine x times itself over 1 equals 1. And this entire left side is one of the Pythagorean identities. It all just equals 1. And so we are able to prove that the left side equals 1, the right side equals 1, 1 equals 1. That is a proof. All right, for 11, sine squared plus cotangent squared x times sine squared x equals 1. We got a lot going on here. Let's start by rewriting cotangent in terms of sine and cosine. So you've got this string of fractions. The important thing is to notice that these are being added and these are being multiplied. So the ones that are being multiplied, when you have factors in the numerator and the denominator, they cancel out. And what you end up with is cosecant squared x over 1, which is just cosecant squared x. And now you can get to the addition part. Sine squared x plus cosine squared x is 1. 1 equals 1. That is one of our Pythagorean identities. two left. All right, these get a little bit tougher. We've got secant squared x plus tangent squared x times secant squared x equals secant to the fourth x. So the first thing I don't like is that 4. And I noticed that every value in here, okay, there's kind of 3 main values in here. All of them I could at least take a secant squared x out of. All right, I could divide it out or factor it out. So I'm going to take that from all of them. And if I divide everything by secant squared x, this is secant squared x over itself. So that's just a 1. These are being multiplied. So numerator, denominator cancels. That leaves me with just tangent squared x. And then on this side, I've got the 4 and the 2. When you are dividing exponents, you subtract them. And so that leaves me with secant squared x. Now this entire left side is one of the Pythagorean identities using your 7s, and it equals secant squared x. So if the left side and the right side are equal, we have proven it. And our last one, 13. All right, I've got sine cubed x, okay, don't love that, times cosine equals, or cosine squared x equals cosine squared x times sine x minus cosine to the fourth x times sine. So a lot going on here, okay, a lot going on. The first thing I want you to do, it helps to kind of like establish what your different values are. So I'm going to just underline all the ones that are connected through multiplication. They're kind of like bonded together, okay? Notice that each one of them has, and I'm going to do this in 2 steps just so it's not too overwhelming. Each of them has at least a sine x that I could factor out or divide out. So if I start with that, if I start with dividing by sine x, I'm going to start down here on the far end. These two cancel out. So that means all I have is cosine to the fourth x. And I go to the middle. Well, these two also cancel out. So that leaves me cosine squared x, okay? And then on the first, kind of value right here, I've got 1 that will cancel out down here, and that will take one of these away and leave me with 2. So I've got sine squared x times cosine squared x equals cosine squared x minus cosine to the fourth x. So it definitely simplified my problem. And now I've still got a 4 up here that I don't love. And if I look, I've got my first value, my second, my third. All of them could have a cosine factored out. And they actually could all take 2. I'm going to take 2. So looking at my first value here, I've got a cosine squared x over a cosine squared x. That leaves me with only a sine squared x. Then here I've got cosine squared x divided by itself. Any number divided by itself is 1. And then down here I've got 4 and 2. I'm going to subtract since I am dividing, and that will leave me cosine squared x. All right, we're really getting somewhere now. This looks a lot like one of the Pythagorean identities. If you start with your original, sine squared x plus cosine, let me just make that, sine squared x plus cosine squared x equals 1. You could, right here I've got 1 minus cosine. You could subtract cosine squared x from both sides. And now these two look alike. These two look alike. So what that's saying is this whole right side actually equals or can be substituted with sine squared x. And that proves that these two sides are equal. So hopefully this helped you. I know this section was probably the most difficult of all of them. You need to know all of your identities really well in order to prove these things. The important thing to remember is that if the instructions say to prove, you're going to go in with the assumption that these things are equal, and you got to find a way to make the sides match. So I hope this helps you prepare for your test, and good luck.